Welcome again to ThinkTech Talks here on a Tuesday afternoon, this time with Mike Deweert. He's Dr. Mike Deweert. He's our chief scientist. ThinkTech's chief. Every company ought to have a chief scientist, and we've had Mike as our chief scientist since long ago, probably 10 more years
maybe
ago.
Even 12 or 13
maybe
years.
12 or 13, and neither of us, well, I don't, he doesn't look any older. I look older. Mike is a scientist with BAE Systems, and he joins us today to talk about, well, I guess science. Now, you know, as we left it the last time, which was, what, 3-4 weeks ago, we were talking about the 18th century. Mike, can you first say hello to them?
Aloha.
And then tell them where we left it in the 18th century last time.
Oh, where did we leave it? We left it with, if we had to go back to the 18th century, that kind of living, how could we do it? Could we do it? And I think we left it at, there'd have to be a lot fewer of us, which wouldn't be a good thing for most.
Some of us could, and some of us couldn't.
Yeah. And we had talked about some of the inventions that we've always been a technological species, how the Romans invented concrete, and that we kept on through the 18th century. Now, the 18th century ended up being sort of the nascence of science. The scientific method was kind of born then, and has given us a huge advance in our prosperity since then.
Yeah. Well, it's become, maybe it's displaced in some way religion. It's become, the mantra for the Western world, well, for the whole world. And people swear by it, and they see optimism in it. They see the future in it more than any other single thing that you can have. I mean, and that has pervaded since the 18th century.
Yeah, that optimism, a sense of progress, that we're getting better. And some of it World War II kind of changed that a little bit in the sense that you had the atomic bomb and people got pessimistic.
Yeah.
About it because they could see that there's both good and harm that can come from science. But it's up to us to choose, the good, the things that will benefit the species.
Well, let me throw one at you. The more we believe in science, the more we believe in improving the condition of humanity, the happier we are. The less we believe in science, I mean, if we get doubtful about science and see the dark side, or if we abandon it in favor of other things, other paths, if you will, then we lose that optimism.
Right.
Science is optimistic because science means finding things we didn't have before.
Yeah, it's based on the fundamental hypothesis of science. The founding principle is the universe is understandable, even if we don't yet understand it, and that we can eventually understand it. And that's what Einstein said, that the most incomprehensible thing about the universe is that it's comprehensible. And that's incredibly optimistic. We're not at the whim of forces of nature. We can predict hurricanes coming now. It used to be the storm would start coming, we'd huddle in our grass huts or get killed, but now we can see these things coming, we can predict them better and better, and that's what science is about, giving us a way to predict nature and ultimately control how nature affects us.
But we will get to the principal discussion of the show. That's Michio Kaku's book is actually copyrighted in 2011. Called The Physics of the Future, How Science Will Shape Human Destiny and Our Daily Lives by the year 2100, which is coming soon. But before we do that, I'd just like to ramble with you just for a moment about things, that are happening. Climate change. We've heard so much, and West has been here at this table so many times. And, we seem to be able to maybe ameliorate it with scientific ameliorations. But we don't have the political will. Where does this fit in the mind of a scientist?
It's frustrating as all heck. I mean, I tell the people in the environmental caucus that, we've lost the battle to prevent global warming. Global warming is going to happen. The question is how much global warming and how quickly, and how do we prepare for the consequences and shield ourselves as much as possible from the negative consequences. We know there'll be more hurricanes. We know that the sea level will rise. It's not perhaps as catastrophically quick as some people have painted it. I mean, here in Hawaii, we'll see 3 feet of sea level rise by the year 2100. That's not catastrophic unless you happen to have beachfront property, but you will see more storm surges. And the question is, do we continue to armor the coast, put up more seawalls, or do we retreat from the coast and admit that nature is, stronger than us still when it comes to, the consequences of our own actions on the climate. We could switch as quickly as we can to cleaner energy, and we're trying to do that here in Hawaii. Solar energy is about the cleanest you're going to get. And you could also switch to forms of nuclear energy that are clean. The first nuclear fusion reactor, the International Thermal Nuclear Energy Reactor in Europe, will be coming online in about 2020. Now that will be a research reactor. It'll make about 0.5 gigawatt of power, which is a pretty good sized plant, about 2/3 what Hawaii would use. It won't be on their grid yet. They'll be studying it to learn how to build a real thermonuclear fusion reactor, but that's one of the clean sources of energy that we could use. The first,
and real cheap.
well, it will be. There's enough deuterium in the world's oceans to power civilization for the indefinite future. Will it be cheap? That's a good question.
Well, once you get over the initial cost of building the
right.
plant, but
yeah, once you get over the first cost of building the plant, but you have to invest billions of dollars right now to build any other kind of power plant. And what we're not accounting for right now is the cost of ameliorating the climate change that greenhouse gases are causing. Those should have been factored into the cost of every fossil fuel plant ever built in the past. Mm-hmm. They weren't. And now a whole society is going to be paying for it. And trillions
more than
of dollars.
Just the dollars and cents at the beginning.
And human suffering and trillions of dollars of effort to move cities away from the coast. Here in Hawaii, our average elevation is 3,000 feet. Florida average elevation is 100 feet. Florida is going to have to be abandoned if sea level really sets in the next couple centuries, and that will cost trillions of dollars.
Yeah, but I mean, you make it sound so monetary. In fact, lives will be changed.
Oh yeah.
Who knows? You can't even predict all the things that will happen.
Sure. So instead of refugees from the cold north moving to Florida, you'll have refugees from climate change moving from Florida back north.
But cheer up, it'll be warm in the north.
Right, but the socioeconomic dislocation, you're right, the disruption of lives, the disruption of nations, the disruption of civilizations. Tuvalu is going to disappear, Kiribati is going to disappear. Island nations of the Pacific, a lot of them is going to be gone. And where will those people live?
And our values will change. What really matters will change, and maybe we'll have contention over that. Yeah. And maybe we'll have disruption to just about everything, even though we don't predict it. Even though we can, we can make some calculation on the dollars, but the secondary effects are the ones we can't calculate.
And a lot of that can be mitigated by the science can predict a lot of things like which nations will go underwater first, and what the carrying capacity of certain nations where they might become refugees are, which nations could best take those refugees with the minimum disruption. We can predict that, but generating the worldwide, it's going to take worldwide political will to really make this as least painful a transition as possible. We will have sea level rise, we will have global warming, we will have crop failures, we will have more hurricanes. We can deal with this. It does not have to end our civilization globally, and we can mitigate the consequences, or we can fight over who has to pay and make the consequences worse for ourselves.
It's biblical,
it's amazing. It's amazing.
It's will mankind cooperate with each other, or will they, destroy each other?
Yeah. Right. We can if we cooperate with each other, there's no limit to what we can do. I mean, there's no law of physics that says our civilization has to end.
You heard it here. Okay, well that's encouraging.
Oh, no, I mean we can move up and move our cities inland.
It's so interesting. It couldn't. Yeah. The funny thing about this continuum is post the 18th century. We've done amazing things, but we've also despoiled the environment. Yeah. And now, when the environment is about to bite us, it is biting us back. I mean, who knows where the storms will come from tomorrow, we do, at least theoretically, we have the science to deal with it, we think. Yeah. And so all is not lost, because what's taken us here gives us tools to deal with the problems we have created. Yeah.
Interestingly enough, like for example, energy. People talk about an energy crisis. We have plenty of energy. We have energy for 3,000 years just in what we know how to exploit. In terms of, now we could burn fossil fuels for another few hundred before we run out, and that'll make our problems worse. We could burn uranium for another 30 years and power a whole civilization that way, and that'll make our problems maybe a little worse, maybe a little better. There's ways to burn up the uranium fission products in a way that produces more energy and reduces how long those things last. So we can reduce how long we have to watch those from hundreds of thousands of years to hundreds of years, which is within the realm of a civilization. We can move over to fusing thorium, which would give us, fissioning thorium, which would give us fuel for 3,000 years. And thorium's dirt cheap, literally. It's a thing they have to get rid of in certain areas because it's an annoyance. That would be easy. And eventually nuclear fusion. Nuclear fusion's been 20 years away for the last 50 years. And the first fusion plant that might actually produce a lot of power is, 2020. That's when they predict it'll come online. But ultimately, that could be the solution. Nuclear fusion for cold northern climates where they don't have much sunlight. You could fuse deuterium and produce all the energy you need for grow lights in those northern climates. If we can't farm in the south because of the droughts and the desertification, we still would have the energy to farm in the north, even in the winter. So there's hope there. We can do this.
Okay, I need to take a break just so I can integrate all the things you're saying. Coming at you fast. That's Mike Deweert. He's our ThinkTech chief scientist. He's actually with BAE Systems. This is ThinkTech Talks. I'm Jay Fidell in the Tuesday 3 to 4 block. When we come back, we're going to talk about what is fusion.
Oh, okay.
That's the first thing.
Okay.
The second thing is we're going to talk about the role of the scientist in a world that needs to be saved by science. We'll come right back after this break.
We want to thank our underwriters.
Hawaiian Electric Company and its affiliates Maui Electric on Maui and Hawaii Electric Light Company on Hawaii Island are deeply committed to the communities they serve.
Galen Ho is a senior executive of BAE Systems, a global defense, security, and aerospace company.
The High-Tech Development Corporation, the state's leading technology agency, attached to the Department of Business, Economic Development, and Tourism.
Castle and Cook Hawaii, with a time-honored legacy that spans more than 160 years and revolves around its mission of investing in Hawaii, creating communities, and providing for the needs of our state.
Hawaii Gas, formerly the Gas Company, a proponent of the Liquefied Natural Gas Initiative, helping Hawaii achieve its transition to clean energy and a better energy future.
Collateral Analytics, a Hawaii-based tech company empowering the real estate industry with greater and faster access to the tools and data they need to make better informed property investment decisions.
I'm Nicole Horry. Thanks so much for joining us on ThinkTech.
I'm Maria Kashem. See you next time.
We're back, we're live, we're here on ThinkTech Talks. I'm Jay Fidell. We're talking with Mike Deweert, Dr. Mike Deweert, who is our ThinkTech chief scientist from BAE Systems. And we're talking today, of course, about science. We ultimately will get to the subject, the principal subject, which is the physics of the future, in a book written by Michio Kaku. But just warming up, again, you spoke, and you have spoken before about fusion, nuclear fusion. Yes. And we have had other guests on the show from the university, from physics, who talk about nuclear fusion. But, that's on the far side of nuclear as we have seen it in the Second World War and as we have seen it in power plants. What is nuclear fusion?
Well, okay, so nuclear, we can make energy by nuclear fission and nuclear fusion. Nuclear fission is to take a big heavy nucleus like uranium and induce it to split, and that releases energy. The other end is nuclear fusion. We take very, very light atoms like hydrogen and jam them together to make a little heavier atoms like helium. Turns out that when you fuse hydrogen to helium, you have a great big energy gain. The neutrons and protons like to be stuck together in groups of 4 in a helium nucleus. So a helium nucleus is 2 neutrons and 2 protons, and that is so stable, it's almost impossible to break. Next most stable thing is deuterium, which is 1 proton and 1 neutron. That's heavy hydrogen.
And deuterium is the second element on the table of elements, right?
Well, it's an isotope of hydrogen. So hydrogen's
Okay.
the first one. It's one proton, nothing else. Deuterium is one proton and one neutron. It's heavy hydrogen. It's stable, very stable. Most of the deuterium in the universe is made in the Big Bang. And there's very few other ways to make deuterium, and it gets consumed because it's very easy to take two deuteriums, jam them together, and make a helium nucleus, and that releases a lot of energy. And that is one of the easy ways to nuclear fusion. Now the sun has burned up its deuterium mostly. What the sun is doing is it's using the force of gravity and heat to jam hydrogen nuclei together. And it's a complicated, long process, but eventually 4 hydrogen atoms, 4 protons, get jammed so close together that the strong nuclear force takes over. So
The sun is a nuclear
it's
reaction.
a nuclear reaction, a fusion reactor. And the reason it takes so much gravity is because protons and deuterium and nuclei are charged positively and they want to repel each other. Now that repulsion is a long-range force. They can feel that repulsion from a long way away. There's also something called the strong nuclear force. The strong nuclear force is a very short-range force, but if you get them close enough, it's much, much stronger than the electromagnetic repulsion. And if you can overcome that electromagnetic repulsion, what scientists call the Coulomb barrier, and get the nuclei close together, they'll fuse to each other. And in the intermediate, and the reason it's hard with hydrogen is that in the process you've got to convert a couple of protons to neutrons, and that's done via the weak nuclear force, which is stronger than electromagnetism, but much, much weaker than the strong nuclear force. You've got this long chain of processes to take 4 protons, jam them into one helium nucleus. But if you can do that, you generate a lot of energy per reaction. Now in the sun, this reaction...
Just hold the thought.
Yeah.
There's going to be a short examination about this right after the program.
Yeah,
Look at our website, and you'll be able to just write to me. We'll get jay@thinktechhawaii.com. Get the examination. And if you win this examination, you get to come on the show and ask Mike Deweert any question you want about fusion.
I may not be the best person to answer them, but I will try.
Okay.
So
Go ahead.
So when you look at, if you were to look at what the physicists call the curve of binding energy, where you look at all the elements in the periodic table and you look at how much energy there is holding them together. Hydrogen, call it 0 because it's not held to anything. Helium is way down here, and then the next one up, lithium, is way up here, and then it goes up and up and up until it starts to come back down again, and the minimum is around iron. So, but helium, there's a big difference in energy between a free proton and a helium atom. There's a big difference between a proton and a deuterium, which is 1 neutron, 1 proton, heavy hydrogen. There's a big difference between deuterium.
Heavy water.
Right. Well,
Okay.
Heavy water would be...
It's a product of heavy hydrogen.
Right. Heavy hydrogen combined with oxygen will make heavy water.
Okay.
Okay. And then down here is helium, which is very, very tightly bound. So in the sun, it's fusing protons to make, through a long chain to get down to the helium. And in the sun, that reaction goes very, very slowly. Every kilogram of the sun is producing a very low amount of energy, about like you and me sitting here. I mean, we're producing more energy per pound than the sun is.
Okay.
Believe it or not.
I
It's
feel
just
it.
burning chemical energy. And it's not that the sun is so efficient as a reactor, it's that there's so much of it. There's a huge star out there, a huge mass, fusing at a pretty low rate, so it's going to last us billions of years. But it's so inefficient, we couldn't possibly rely on it on Earth for our energy. We'd be better off just burning fossil fuels. I mean, it would be much more efficient. So what they're trying to do is trying to trick the nuclei to fuse more efficiently here on Earth. Now, in a nuclear bomb,
Tricking Mother Nature.
tricking Mother Nature. So what they do in an atomic bomb is the fission bomb, the splitting of the uranium atoms or plutonium atoms, releases a lot of energy, and some of the energy comes out in the form of gamma rays. Now, next to that fission bomb, to make a fusion bomb, what they do is they put the deuterium and tritium mixture, and I'll get into tritium in a minute, but they put a mixture of 2 isotopes of hydrogen together, and they surround it with a material that absorbs gamma rays, like polystyrene, plastic. And this is the famous Ulam-Teller configuration. So the nuclear fission bomb goes off, and the shock wave wants to blast apart the whole thing, including the fusion core. but the gamma rays get there before the shock wave does. The gamma rays are absorbed by the plastic heats up, squeezes the deuterium-tritium mixture, these isotopes of hydrogen, and before they know what's happening, they're all so close that they start fusing. And before they
Then you get fusion.
And then you get a nuclear fusion reaction.
That's the way you started.
That's the way you start an uncontrolled nuclear fusion reaction. So we've tricked nature. We don't have to heat up a plasma and confine it to make it steady state. We just jam them together before they know what's happened, while they're still out of equilibrium. We jam them so close together they start fusing. They see each other's strong nuclear forces and fuse.
And all this with some plastic.
With some plastic, polystyrene. Yeah, like I said, the famous Ulam-Teller configuration.
Okay.
Invented independently by Sakharov. And so, so we've been trying since then to figure out how to control this reaction, make it run slowly and in a controlled way, so we can actually use the energy productively.
Why do you like fusion better than fission?
Well, fission. Well, I don't like, it's whatever's effective is what you want. Now, the problem with fission is with the heavy uranium atom, so most of our fission we make with uranium-235, a rare, sort of rare isotope of uranium. Uranium-238 is got a very, very long half-life, billions of years. Uranium-235 is much shorter half-life, and it's a small fraction of all the uranium. Uranium-235, though, will fission. You hit it with a neutron, it will split into two smaller nuclei, but they're still pretty heavy. They're still heavy metals that are toxic. And they also tend to be radioactive heavy metals with long half-lives. So you take your uranium atoms, you can get a chain reaction going where uranium atom splits, releases two big fission products and several neutrons. Neutrons go on and catalyze other uranium fission reactions. And now you're left with this. So you get a lot of energy out. It releases a lot of energy because everything wants to go to iron. Iron is the most tightly bound thing there is. Helium is too far away from iron, but iron's the most tightly bound thing. So the uranium atom.
I mean everything's together. It's all connected.
The iron nucleus, the protons and neutrons in iron nucleus are more tightly bound to each other than in any other nucleus.
Okay.
They're very, very happy. Iron-56 is just the happiest isotope there is.
That means it's stable.
It's very stable. Yeah, right. Once you're to iron, so stars can only make things heavier than iron by supernova explosions, where they start jamming the iron nuclei together and make. It costs energy to do that, but you end up with heavier isotopes. But in normal stars where they're fusing things to generate energy, it ends in iron. Iron is the most stable thing there is. So in a supernova explosion, you generate uranium and plutonium and things heavier than iron, like thorium as well, and those then coalesce over the next generation of stars into planets and new stars. So we are star stuff. We are the product of supernova explosions. Everything heavier than iron around us came from supernova explosions. And most of what's not heavier than iron is only available to us because of supernova explosions. Stars spewing their fusion products into space and then it becoming our planet eventually. And here we are. So in fact, we owe our existence to nuclear fission now, as well as fusion. The sun powers our planet, the life on the planet, but the Earth's magnetic field is generated by the molten core of the Earth. And
Which is also a nuclear process?
What's happening is that the Earth's core should have solidified by now. After 4.5 billion years, it should be solid iron, no magnetic field, no spinning dynamo generating this field. But what is keeping it liquid is nuclear fission, or radioactive decay. Small amount of fission, mostly radioactive decay of radioactive isotopes that live a long time. Uranium-238 lives a long time. It provides about 40% of the energy. Thorium-232 has a 14 billion year lifetime, about the same lifetime as the universe. It's providing about 40% of the energy. There's a lot of other radioactive elements that together make up the rest. Because of the Earth's crust is a good insulator, it keeps the heat in, and the Earth's core stays molten, powered by this liquid, nuclear radioactive decay things like thorium and uranium.
How deep is it? I mean, how much would you have to...
It's mixed throughout the whole mantle and the whole core.
If I went down
well.
100 miles, would I find it?
Oh, there's plenty of uranium and thorium in the crust.
No, I mean heat.
Oh, heat. Oh, yeah, sure. The deeper you go, the more heat you'll find.
So, I mean, it's just a digression. We're going to come back to the question, but...
That's why the lava is molten when it comes up.
So geothermal, we have sort of an example of that, but I mean, isn't it so that if you go down and you find all this heat, you have an unlimited supply of heat, that is energy, for mankind to use forever and ever and ever.
Absolutely.
And it wouldn't be limited to geothermal, it'd be all kinds of things.
Hard to exploit because there's only a few places where that heat comes close enough to the surface where you can actually easily exploit it, like Iceland, New Zealand, Hawaii, parts of California, Yellowstone. Of course, Yellowstone we want to preserve as a park, and there's parts of Hawaii we want to preserve for the cultural and natural value. But there's also places where we can easily exploit the energy and use it to power our civilization.
As our technology gets better, we can go further and we can exploit it in more places. So, I mean, if you're worried about running out of energy, we're never going to run out of energy.
There's no reason for us to run out of energy.
Okay, so let's go back to the question. The question was, what's the difference between fission and fusion, and why do I prefer fusion?
All right, so fission, like I said, with fission, you're taking heavy nuclei, you throw a neutron at them, it absorbs it, become unstable, it splits into two smaller nuclei. But these smaller nuclei tend to be unstable and have long half-lives, so you have a lot of radioactive material as a result. And with fission, you get some energy, but you get a lot less energy per pound than you would with fusion, so you end up with a lot more radioactive material to deal with. And wherever you have neutrons, you have the chances that the neutrons will be absorbed by whatever vessels containing that, and that can become radioactive through its neutron activation. So you end up with a lot of radioactive iron and radioactive concrete that you got to deal with. So with nuclear fusion, ideally, if you just took two deuterium atoms,
it's simpler.
It's simpler if you can jam them together close enough that they overcome the electrical repulsion and see the strong force. These two deuterium atoms, which is each one proton, one neutron, can fuse to become a helium atom, two protons, two neutrons. And in the process, helium is safe, inert, not toxic, it's stable,
easy to take.
And it releases a lot of energy.
You could have some, it would make you lightheaded. I'm going to tell you.
And it would give you a squeaky voice, too, like Mickey Mouse.
Never mind.
That's a whole different, that's the physics of the sound propagation in a gas, you know. So, but back to the physics of fusion. So the problem with fusing two deuterium atoms is that you've got to, if you try to shoot them together like two bullets at each other, they got to hit head on to fuse, because you've got to conserve not just energy, but you've got to conserve momentum. And if they hit head on, they might fuse. If they hit at a glancing blow, well, then now there's no way for them to conserve momentum. They'll bounce off of each other, or they'll fuse and you'll waste a lot of energy because they'll have to do something. Well, they probably won't actually fuse.
Okay.
So what they usually do in a fusion reaction is mix in what's called tritium. Tritium is a heavier isotope of hydrogen. It's one proton and two neutrons. It has a half-life of about 12 years, and it decays to helium-3. So tritium, what happens when you take a tritium nucleus, which has one proton and two neutrons, and try to fuse it with a deuterium nucleus, you have now a helium plus a proton. A helium plus a neutron. Now that neutron can carry away the momentum of the reaction. So this reaction goes much more easily. Tritium-deuterium fusion takes much less of a squeeze and a push to make happen than deuterium-deuterium.
Okay, well, I'm
which would be
encouraged
perfectly
by
clean.
that.
So
I want to, we're going to take a break now, but before
right.
we take the break, I just want to say that, it's great that ThinkTech is on the internet. Because you can see it over and over again. Right. And in case you didn't catch everything that Mike Deweert said, you could listen to it over and over again. And after a while, you learn physics. It would be an extraordinary thing to listen to this enough so that you actually have a comprehension of it. So we're on Ustream.tv, we're on Spreaker.com. Our stuff is posted on YouTube, and ultimately we show in Olelo. So it's there for you, and in each case, you can listen to it over and over. This is Mike Deweert. He's our chief scientist here at ThinkTech. He's also a scientist for BAE Systems here in Honolulu. We're doing ThinkTech Talks. I'm Jay Fidell. We'll take a minute. We'll be right back. Stay there.
Aloha, I'm Nicole Horry for ThinkTech. For nearly half a century, the Hawaii Foreign Trade Zone No. 9 has brought the benefits of the Foreign Trade Zone program to Hawaii businesses and entrepreneurs. DBET, the Department of Business, Economic Development, and Tourism, operates Hawaii's Foreign Trade Zone program to encourage international business and economic development. The Foreign Trade Zone's mission is to increase the amount of international trading activity in Hawaii, thereby providing employment opportunities for the residents of our island state. For more information, see ftz9.org. I'm Nicole Horry. Mahalo.
We're back. We're live. We're here with Mike Deweert, our chief scientist here at ThinkTech. He's also with BAE Systems. We're doing a ThinkTech Talks with him. We're really enjoying this a lot. And let me say, you know, you can say, I was watching this and he was talking about physics and deuterium and whatnot. But you know what? Where else are you going to get this? Okay. Just try find anywhere on the dial that a scientist would talk to you at his own level of science. We here at ThinkTech encourage scientists to talk to you in their own language, you know. Yeah. And if you've never heard a scientist talk, you're hearing one today. You know, Mike is letting you into his world. It's different. It's not, you know, he looks like an ordinary guy, but anyway, so I wanted to ask you the next question.
Sure.
And we can come back to the specifics of energy in a while, but you know, all of this suggests, as since the 18th century, updating our discussion, the scientists have more knowledge, more capability, they're right more of the time. They've studied these things, and through the scientific process, you know, of discovery, you know, they know a lot more. And the question is, what is their role in modern society in delivering all they know and making it work for humanity?
Yeah, because you have the positive things of science. Of course, we've wiped out the smallpox. We've almost wiped out polio. And the only thing that stopped us from wiping out polio is people who deny science, people who are hostile to science. It's a few countries in the world remaining. There's only 3 countries where polio is still endemic, you know, Pakistan, Afghanistan, and Nigeria. And it's come back in Syria because of people from Pakistan going there to fight in the war there. And the only reason we haven't wiped it out in Pakistan and Afghanistan is the hostility of certain elements of society. They think it's a Western plot of some kind, which is astonishing to me, because in the rest of the world, people have benefited so much from polio being wiped out. You'd think the benefits would be obvious, but it's not.
You can find it on the internet anywhere in the world immediately. In 10 seconds you can find it, but they don't believe it.
They don't believe it, and yet, so, I mean, I was born, like, you know, the first year the Salk vaccine came out. And before that, I'd had the Sabin vaccine, which is not a killed polio, it's an attenuated polio virus, which allows you to spread the immunity to your little playmates as a child, but it has some chance that it will revert to wild type. So in the first world, they prefer the injectable killed virus vaccine instead of the vaccine you can ingest. And we've learned a lot about that now. We've learned, like I say, we've learned how to wipe out polio, and we know how to do it. It's only a matter of political will now. We've already wiped out smallpox. And, you know, the countries of the world, there are a few countries of the world that probably still have stockpiles of smallpox in freezers for research, but if they ever let it get out, that would scourge to be back. So is there political will to destroy those stockpiles, for the countries to trust each other to destroy those stockpiles?
Yeah. So
we learn how to, there's a lot of positive things, like electricity. We've harnessed electricity. You know, a modern city can't live without electricity now. It's unthinkable that we would try to build a city without electricity. It provides us light, communication, heat, everything. it's high quality energy. We don't have to go gather firewood and chop it.
Well, it goes back to your comment about what would happen if we didn't have the science in the 18th century, of the 18th century. And the answer is there'd be a lot fewer of us because most people would die for the lack of the science.
Right.
And I mean, that possibility remains. I mean, if you fight with science, you're fighting with yourself.
Yeah, like in the early 1900s, there was a crisis of food production in Europe because of a lack of fertilizer. Nitrate fertilizer was hard to come by. They couldn't make enough manure from horses and cows and stuff to fertilize the fields to feed their growing populations. Chile was incredibly rich because it had all these phosphate and nitrate reserves in mines from ancient deposits of Battenberg guano. But there was a crisis because they're running out of those things, getting expensive, and the war intervened and stopped shipments to Europe, and Germany was looking at starving. Kaiser made a prize. Whoever can find a way to make nitrate fertilizer without guano or dung or whatever would become rich. And a German scientist invented a process, the Haber-Bosch process, for catalyzing the fixation of nitrogen using fossil fuels. He used uranium as a catalyst to make ammonia from nitrogen in the air. And so now we have no shortage of fertilizer. We know how to make it now. The Haber-Bosch process now doesn't use uranium as a catalyst anymore. It uses other catalysts that are cheaper.
And without it, we couldn't have the fertilizer. Agriculture would change for the worse. People wouldn't get fed.
Right.
So this is pretty scary. And so what I just worry that the political side of the equation may not respect the scientific side of the equation, and it's a tenuous balance sometimes, and sometimes science loses. That's in Afghanistan, Pakistan, what have you. So how do we solve this going forward? It's like there should be a science department in every government,
There should be a science department that actually, it has some clout. But the problem is scientists they want to do science. They don't want to fight people.
They just want to research. That's all they want to do.
They want to make progress. And sometimes fighting these rearguard actions against people who deny the value of science just because they don't like what it's saying. The politicization of scientific conclusions is a problem. For example, with global warming, there are certain moneyed interests that don't want to have to stop burning fossil fuels, and will fight mightily. It was like when it's similar to when the science said that tobacco was killing people, and the tobacco industry said, no, it's not killing people. No, tobacco is good for you. We have doctors who will tell you tobacco is good for you.
That's really dirty business.
It took decades. It took decades for the moneyed interest to finally, be overcome by the sheer weight of scientific evidence and public opinion, and still,
some people don't accept it.
Right.
and look at climate change. I mean, it was within the time I met you. That Al Gore came out with this movie. It was within the time I met you that there were sitting legislators in our Congress who denied climate change and who attacked anyone who advanced the notion.
There still are.
That's terrible. We won't name names, but it's really frightening. So the question is, can we make proper? And this is pretty risky business if we deny the science that can save us. As climate change and disease and agriculture and all these things. It's time to get on board with science.
I think so. And the science denial isn't a problem just on the right. It's a problem on the left too. For example, there's genetically modified rice that produces vitamin B that is in short supply in the third world. People are suffering vitamin deficiencies. We have a golden rice variety now that can supply those deficient vitamins. But there's a whole anti-GMO movement that would say, you can't use that, that's a frankenfood. Well, okay, it's a tool to help people. And you have a philosophical objection, well, find another way to help people. Find another way to get the vitamins to them in a way that, or you accept that this is a tool of science that can help. There's a lot of things, like with the nuclear energy. There are people say we will never use nuclear energy. Well, your choices right now are to burn fossil fuels,
which is going to get you in the end.
Which will get you in the end.
Sooner, actually.
Right, actually sooner. Yeah. So, it's another tool that could help us, used rightly. Now here in Hawaii, we don't need nuclear energy. We got so much sunlight coming down that it would be fools not to use it. And the breakthrough we would need here is a breakthrough in energy storage technology, better batteries, or a more efficient way to break water into hydrogen and store the hydrogen and burn it later, those kinds of things.
Well, what's interesting is that I wrote an article recently and I identified all the tech advisory councils that have come and gone in the past 10 years or so. And there have been a few of them. Right. And they've all come and they've all gone. And at this moment, there is none. Yeah. And you wonder what the nexus is, between government, which is supposed to be running the operation, and science, which can tell you pretty well how to save the operation.
Right.
And there's something missing if the government doesn't have a tech council and is not listening to scientists, and they have to find their own advocacy. Right. That's what happens. Right. They have to come. They have to say, I want to come to the city council or the state legislature. I am asking you to tell you my science. Right. It should be just the other way around. Right. Yeah. But let me take a break.
Okay. Right.
This is a wonderful conversation. Yeah. That's Mike Deweert. He's our chief scientist at ThinkTech, and we have fabulous conversations. He's with BAE Systems. This is ThinkTech Talks, having a wonderful time on a Tuesday afternoon. When we come back, we are going to get to our ultimate discussion. Okay. This is Michio Kaku. Physics of the Future, How Science Will Share Human Destiny and Our Daily Lives by the Year 2100. And we will find out, among other things, why Mike Deweert brought this book to the studio.
Okay.
We'll be right back. Aloha, I'm Jay Fidell. This is ThinkTech Hawaii, broadcasting live from the Pioneer Plaza in downtown Honolulu. We raise public awareness about tech, energy, and globalism in Hawaii. Technology is critical to our state. A vibrant tech sector will give us new prospects in the global marketplace and will offer great careers and make our economy more resilient. Streaming live on Ustream and Spreaker, ThinkTech allows its hosts and guests invaluable opportunities to report important events and discuss important questions, and to be heard here in Hawaii and around the world. You can find links to our live streams on thinktechhawaii.com or on our mobile website, m.thinktechhawaii.com. And you can see our archive on YouTube. It's all just a click away. We want to do whatever we can to keep Hawaii relevant, connected, and thriving in the complexity of the 21st century. We hope you will help us in those efforts. Tune in today. This is ThinkTech. I'm Jay Fidell. Mahalo. We're back. We're live. We're here with our chief scientist, Mike Deweert, who is also at BAE Systems on ThinkTech Talks here on a given Tuesday in the 3 to 4 block. And we would be remiss in our duty to explore the universe if we did not mention that Mike brought a book with him that is The Physics of the Future by Michio Kaku. Yeah. And what is interesting to me about this is that Michio Kaku has written several books about science and trying to sort of make it relevant to everyone.
Oh, yes.
And he is teaching at the City University of New York, of which I am a product.
Really?
Yeah.
I didn't know that.
Yeah, now you know.
Okay.
So tell us, why did you bring this book here?
Well, Michio Kaku has written a book about the year 2100 and how our civilization could look then. And it'll look different. I mean, for example, New York City will be underwater. He predicts that. And there'll be big seawalls built to protect the highest value parts of our coastal cities. But he also predicts by then we'll have nuclear fusion controlled, and there'll be nuclear fusion plants all over the world producing more power than we could possibly use.
Wow.
And those plants by then, so right now you're looking at the physics, and it's hard physics, hard engineering.
Is it harder than your discussion a little while ago?
Well, it's pretty hard. When you look at the plasma physics they're trying to do in Europe at the ITER, the International Thermonuclear Energy Reactor, the first power plant that will actually be producing useful power coming online in 2020 or so. And it won't even be on the grid. They'll just be using it to study how to get on the grid.
Yeah, but who knows from there?
But from there, within 20 years after that, you could have fusion power commercially available. And that would solve our energy problems. There's so much deuterium in seawater in the world that we would never, it would be hundreds of thousands of years before we'd run out of energy based on that. And actually, once we learn a more efficient way to store solar energy, we're good for 1 billion years.
Yeah.
So energy won't be a problem then. He also predicts very amazing things like programmable matter. He predicts like you have little you might have a table made out of these little nano materials that stick to each other and can be reprogrammed to stick in a different shape, change their texture, change their color.
So this is make anything that
done.
way.
Right, you type a few buttons on your keyboard and your table will morph into a chair. Or
I think I saw this on Star Trek.
Right. Programmable matter has been a theme in science fiction for a while, but Michio Kaku talks about some of the research that indicate it might actually be feasible, physically feasible, maybe not economically in the long run, but physically feasible to make programmable matter. And so if you don't like the color of your sofa, you can tell it to change color. Or if you wanted to turn into two ottomans and a chair, you can make it two ottomans and a chair. He predicts things like we'll have, instead of having to use rockets to propel us into space, we'll have built a station 23,000 miles up in geosynchronous orbit with essentially a large rope that heads down to Earth. And so it's in geosynchronous orbit, so it stays at the same spot above the equator, and you just
it's like
go
a
up and down.
beanstalk. It's a beanstalk.
It's like yes, but it takes you up to orbit via essentially a space elevator.
Great.
And it would make getting to orbit so much cheaper.
Yes.
And you could have actually tourists going up there to view the Earth from 23,000 miles up, and but then it makes it easier to get your communications satellites up. Makes it easier to get everything up, because right now the problem with space travel is it takes a lot of energy to get up, and it takes as much energy to get down again back to Earth safely. And you can dissipate that energy of getting up with a heat shield or something, which is a space shuttle solution, but you can't get it back. It's gone. With the space elevator, you can arrange it so that when you're coming down, the force of you coming down drives a dynamo that generates the electricity. It gets back a lot of the energy that you spent getting up. It's like the electric car. When you're going downhill, the brakes generate electricity and charge up your battery again. So the space elevator would work the same. So now we can get our communication satellites up into space. We can actually have a space station that we can get to economically and do research on, or maybe even launch expeditions to other planets, to the other stars. Who knows?
Who knows? Maybe a beanstalk to other planets too. Wouldn't that be something?
Right.
Wow.
He predicts inventions in robotics, like our robotic assistants will be way more capable than they are now, and they'll be on the verge of actual intelligence. He has to predict by the year 2100 that we'll have true artificial intelligence. We'll have robotic assistants that is actually useful. You can change your bedpans in the nursing home so humans don't have to do that anymore, or it can do things that would be too dangerous for humans or too difficult for humans, or humans just don't want to do.
Yeah. All the science fiction movies would come true.
Right. He does predict there will be close to an emergence of artificial intelligence, but we'll probably have a problem with it by the year 2100 still. But we'll get past that. And then he predicts things like, for example, we could have flying cars, in the sense that we could put magnets in the roadbed, essentially have maglev cars instead of just maglev trains.
Yeah, why not? Safe, actually.
Yeah, well, it's less friction, less wear and tear, the parts would last longer.
Less energy.
Less energy wasted to the rolling resistance and friction.
Yeah.
And so we'll have maglev cars floating along magnetized roads. It'll be the end of the age of the internal combustion engine. We won't need to burn fossil fuels anymore. So there's a huge amount and the biggest thing it's predicting is that biotechnology advances. We'll find ways to keep the little telomeres on the ends of our chromosomes. Right now we think part of aging is that telomeres act as little shoelace ends that keep your chromosomes from unraveling and getting damaged.
And you can measure them and find out how long you're going to live.
Right. So as you age, they get shorter and shorter, and it tends to then increase the rate of cellular damage. You start to lose elasticity in your skin, your organs start to wear out. Because right now, actually, you've replaced yourself 3 or 4 times already in your lifetime. Your cells aren't the same as they were 10 years ago.
I feel it.
Right. So we were always replacing, but every time you do replace a cell with, a cell replicates to make another skin cell or another liver cell or another heart cell, it tends to have little errors, and those errors accumulate and are part of the aging process. Well, he's predicting that based on what we know about biochemistry and genetics, that we can solve that problem.
Well, you know, it's all so totally optimistic, you know.
Yeah.
And my reaction, I really like tech a lot,
Right,
you know,
right.
is it's great to live in a time where tech gives you all these possibilities, and you want to live long so you can
Right.
enjoy
Right.
the possibilities in the future. And the more you can have these visions like Michio, Kaku,
Right.
the longer you
Right.
want to live.
Right.
I want to be there. I want
Right.
to taste it all.
That's right.
Unfortunately, it's going to escape me, but we can dream, can't we? Mike Deweert,
You never
our
know.
chief scientist. BAE Systems, he's a scientist with them too. And this is ThinkTech Talks. We've had a wonderful discussion. We're going to do it again and again, right,
Okay,
Mike?
Sure, Jay. I
Thanks so
enjoyed
much
this.
for
This is
coming
fun.
down.
Thank you.
Aloha. Our next show is Asia in Review with Hung Jiang. So you can talk about pollution in China with James Cook of the University of Hawaii, Manoa. We'll be back in a few minutes with that.